The second part of section 5.4 deals with the net change theorem. And the net change theorem says that the integral of the rate of change is the net change. That is, in symbols, if I look at the integral from a to b of f prime of x dx, this is equal to capital F of b minus capital F of a. Now, this may look familiar to you. I really hope it does look familiar to you, because this is the fundamental theorem of calculus part 2. Fundamental theorem of calculus part 2 says, how do you evaluate a definite integral? Well, you find an antiderivative. Well, if the function here we know is the derivative of capital F, then an antiderivative would be capital F. Plug in the endpoints, plug in the b, plug in the a, and subtract. But that was thinking in terms of just calculating area. This is now thinking in terms of, any function you have. If you know how fast that function is changing, then you can figure out how much change there is over an interval of your variable here. So, for instance here, if we're talking about a velocity function, if I look at the integral from time 1 to time 2 of some velocity function of time, then this should just be the position at time t2 minus the position at time t1, because the velocity is the derivative of the position. So this is saying if I integrate the velocity function, I'm going to see what the difference in my position is from the starting point and the ending point, essentially the net change in position. One example out of one of the problems at the end of the section here. If f of x is the slope of a trail at a distance x miles from the start of the trail, what does this integral represent? Okay. So apparently we're going hiking, and somehow we have a function that tells us how steep this trail is when we're x miles from the start. And so the thing is, what does this represent when we integrate from 3 to 5 of f of x dx? Well, the thing is, if f is the slope of the trail, then f of x is the derivative of some capital F of x, where capital F of x is what? Must be the height function. H-E-I-G-H-T, the height function. That is, this would tell you when I'm walked, X miles down the trail, what is my elevation? What is the height that I'm actually at? Because the derivative of that would then be telling you the slope. The derivative of the height function is the slope. So little f is the slope of the trail. Capital F is the actual elevation. So doing this integral here would find an antiderivative, which is the height function, plug into 5, plug into 3, and subtract. That would be the height at 5 miles down the trail and the height at 3 miles down the trail. So it would tell you, this integral then would tell you the change in the elevation from the 3-mile mark to the 5-mile mark on the trail. Okay. It would be the change in elevation from the 3-mile marker to the 5-mile marker. If you're integrating a derivative, you're just getting the function back with the two endpoints plugged in and subtract. Yes, there's one more thing I want to say about this. Sorry, I was just about to press the done button, but I'm not done. One of the things that this does nicely for us is it also lets us essentially solve initial value problems when I don't know how to take antiderivatives. Let's see if I can spell problems. There we go. So, for instance, suppose I give you the information that, I don't know why it delays sometimes, let's try this again. Suppose I tell you that f prime of x is equal to 1 over 1 plus x to the fourth, and that f of 3 is equal to 1. Okay, so here's a derivative and one point that I want my function to go through, and I want to try to find what's f of x. Right? So I need to take an antiderivative, and then I need to use this initial condition to plug in and find out what the plus c is. Okay? The problem is, I don't know how to take this antiderivative. Honestly, I don't. But, from the fundamental theorem of calculus, part 1, I know that this function, the integral from 3 to x of 1 over 1 plus t to the fourth dt, this function right here will be an antiderivative of this one that I started with. Okay. Which antiderivative? And see, this is the thing. The number down here, we've never really talked about how you choose it. But one of the things I know is that if I choose a 3 right here, then plugging a 3 in for x is going to give me a 0 out. What I want to get out is I want to get out a 1. So if I just put that starting value of 1 and then add on this, then I claim that this is precisely the function I want. Notice, if I take the derivative of this function, the derivative of the 1 is 0, and then I add on the derivative of this thing. Well, the derivative of this thing is just this function with that x plugged in, so it's the one that I want. If I plug in an x equals 3, here and here, then this is 1 plus 0, which is 1. So this function right here satisfies this initial condition, and its derivative is the function that I wanted. So this is the solution. This is the function that satisfies these two conditions. Okay. The choosing of a different number here is just essentially the choice of what plus c am I using. So with a situation like this, when I know the x value of the initial condition and I know the y value, then I just choose this integral here with the starting x value going up to some unknown x. That's guaranteeing that this integral will equal 0 at the starting point, so then I can just add on the y value that I want. Okay. So is this really a solution to this initial value problem? And the answer is yes, it is, but this generally isn't the way we like to write this function. We like to find some other closed form of it, but I don't know a closed form of it. But at least I know that this is it. If I had a computer that I could plug in different values of x and approximate areas, I could get an approximate solution for f of x no matter what x you gave me. So anyway, the net change theorem. This is the fundamental theorem of calculus, part 2.